Do you need absolute value brackets?
Always. Whenever your antiderivative is natural log, and that expression could be negative, it's got to have absolute values.
Okay.
Yeah, always. So we saw that in previous webworks, and so rules that we learn about antiderivatives always apply, even when we do new techniques. So anytime your antiderivative involves natural log, that argument, that thing that's going into natural log, has to be positive. And so if it could be negative, you got to make it absolute value. Okay. So we saw examples like this. So last time we saw something like this. Where original integral I think it was this. It was x minus 2 squared. Is that? Okay, so we've always just put a single letter as your numerator, like just a constant term. And the reason we did that was because these denominators are all considered linear terms, right? So x minus 3 is linear. So a constant is one less degree than linear. And so this is also constant, one less degree. Now, even though this is squared, it's still a linear term squared. So this is still considered linear. And so then, our unknown numerator is we're always going to make it 1 degree less than the denominator. So the unknown numerator always 1 degree less than the denominator. And if you have a linear term squared or cubed or to the fourth, it's still considered a linear term. That's why we still just put C. Okay, so that's the rule for it. So let's see a different. So all the ones we've seen so far have been like this, where we had linear terms or powers of linear terms, which are still considered linear. So we need a new example here. We'll do 10 over x cubed plus 4x. So what are the requirements for partial fractions? The first one is you have a rational function, which is a ratio of polynomials. But then the other requirement is what? What was the other requirement we needed for partial fractions? Do you remember? So it's about the denominator. Oh, okay, yes. So yeah, we're not going to. The degree of the numerator is less than the degree of the denominator, and if not, what do we do first? Long divide first. But then there's still another. Once we have this degree of the numerator is less than the degree of the denominator, there's still one more requirement for partial fractions. The denominator has to factor. So does the denominator factor in this one?
Yes.
Factor out. Just an x, right? And it factors into x times? X squared plus 4. So we're going to think about this thing right here as what? Something over x plus something over x squared plus 4. So what's the degree of x? 1 is linear, therefore we can just put an a up here, a constant. But now this is not linear, nor is it a linear binomial to a power. This is quadratic, okay? This is the first one we've seen like this is quadratic. So we need an unknown expression, or expression that's unknown, that's 1 degree less than quadratic. So that would be linear, so we could do bx, but then we need plus c. We need a constant term as well.
That's only when we have the x's, we need constants.
So your numerator representing the unknown expression has to be 1 degree less than the denominator. Who has that? Is that?
Yeah.
So this one is truly quadratic, so we need a full linear term, bx plus c, on the numerator. This one's linear, so all we need is a constant, 1 degree less. Okay, so then from here, though, everything's the same. So we're gonna what we have to figure out how do we add these two together. What are A, B, and C now? So when we add together, we get 10. Okay, so how do we add these together? Common denominator is x times. Okay, so then we ask, what do we do with this first fraction, top and bottom, to get that common denominator? So then we'd have a x squared plus 4. What do we need to do to the second one, top and bottom, to get our common denominator? Just x. So it would be bx plus c times x. And then we want, in order to find what a, b, and c are, we're going to set that numerator equal to? Yeah, so this numerator here needs to equal 10. So what values of a, b, and c make that numerator equal to 10? So I'm going to go ahead. I kind of, we were short on time, so I kind of streamlined this next part. So I'll go a little slower this time. So we're going to take that numerator and we're going to multiply out. So ax squared plus 4a plus bx squared plus cx equals 10. So all I did was multiply out the numerator, right? And actually, so let's rewrite the 10 as, I dropped a penny. Okay, and so instead of 10, so we write it as x squared and x and 10. And how many x squareds do we have?
0.
How many x's? 0 and then 10. So this is the idea of this. We're going to multiply that whole numerator out and then find the terms that are x squared. So which ones are x squared? That one's x squared. That one's x squared. And so that's going to be, we're going to match that up with the 0x squared. And then, which ones are x? We just have one of those, cx. We're going to match that up with the x. And then, what's left is the constant terms, just one. We'll match that up with that. So then from the blue triangles, our x squared terms, we get the equation a plus b. So let's just keep it in blue here. So the x, we get a plus b equals 0. From our x terms, we get that c equals, that's nice. And then from our constant terms, we get, and that's nice. So this is a real easy system here. We already know what c is, and then we know what a is from this, 5/2, right? 10 over 4. Therefore, b is negative 5/2. And so once you create this system of equations here, any way that you want to solve it is fine, right? So if you can use substitution techniques, elimination techniques. Some of you remember a matrix method from algebra. However you want to solve that to get the values of a, b, and c. That's the bottom line. We just got to get these values of a, b, and c so we can rewrite this fraction in a way that we can do the antiderivative. So we got our a, b, and c, and we're ready to rewrite this. So our integral then is equivalent to what? Integral of 5/2 over x. That's our a over x plus negative 5/2 x over plus 0. That's our c. X squared plus 4. And that whole thing times dx. What kind of function is in the parentheses there? What kind of function do we see that as? In terms of meaning of integral, in terms of meanings of integral, what kind of function do we take the integral of? Rate of change function, right? Rate of change times a little change gives us a little bit of amount, and then we're going to sum up all those little bits of amount. Lots of stuff on exam 1 from those first 2-3 days of all about that stuff. So don't lose sight. We're steep in the algebra here. We're steep in all these techniques. Don't lose sight of the meaning of an integral. Rate function times little change in x gives you little change in y. And when we have limits of integration, we know that that thing gives us what? A total amount of change as x goes from that value to that value. When we don't have limits of integration, we kind of see it differently. What we're seeing this as all possible antiderivatives of that rate function, or all possible quantity functions associated with that rate function. So that's what we have here. Okay, so this is easy. Well, we got 5 halves times natural log of absolute value of x. How do we do negative 5 halves x over x squared plus 4? Do you recognize that?
X squared plus 4 times negative 4.
Okay, so yeah, this was the goal, that you could look at ones like this and kind of write down the answer. You see that this is the result of chain rule. This is essentially, x to the first is essentially the derivative of x squared. So we're going to do the antiderivative of 1 over x squared to the 4th, which is natural log. Here the absolute value bars would be optional because x squared plus 4 would always be positive. So whether you put them or not, it's the same. And we're going to have a negative 5 halves. But we're also going to have what we think about taking the derivative of this and getting a 2x with the chain rules. Therefore, I'm going to need another half. Plessy? Questions on this example before we go on to next set of techniques? Yes, please.
Wait, can it be the natural log of, because I thought for its natural log it can only be like x log. So since it's x squared.
Oh, but the x squared, the whole x squared plus 4 is to the negative 1.
Oh, okay.
Right? So this is like negative 5 halves x squared. So that whole thing is to the negative 1. We know when we undo the chain rule, we do the antiderivative kind of the big one, right? The outside function. Yeah, sorry, x. Does that answer it? Another question? Is there? You good? Okay. Last chance. Okay, so that's partial fractions. If you have recitation today, you'll talk about one more from the web work. Oh, so let me talk about the announcements. So I forgot the announcements. On Blackboard here. It doesn't want to do the external monitor. Okay, the first thing is Jason has set up a Piazza page for you guys so you can be in contact and have discussion about homework and the course. So he's going to head that up. Everyone sign up for that. I guess we're about 50% sign up right now. He's going to, after class, he will edit this announcement and put the link so that you can sign up right here on this announcement. And then he'll be your go-to person for any questions regarding Piazza, and he'll be monitoring it and helping you in those discussions. Okay, so use that; it's a great resource. And then also, I put up. Let's turn this off so it looks like what you have. Okay, so this is what your Blackboard looks like. So if you go down here underneath class videos, first of all, don't forget about the class videos. It's a great way to go back and you can pause and take better notes and review the stuff we've done. Really great resource. And then I just put up the office hour schedule. So now we are set. I am Tuesdays and Thursdays, 9:30 to 11:30 in ECA, which is right there about a minute away across from the bookstore. And then Jason will be in Wexler 303, which is a tutor room for like all math. But he'll be there Mondays from 9 to 10 and Wednesdays and Fridays from 12:30 to 1:30. So please take advantage of help from us in these office hours. We hold these office hours for students, so don't be afraid to come get help, okay? So let's go on to the next technique, which is integrals involving trig functions. So here is a list. So a key component to these trig integrals are trig identities. So here's a list. I'm going to post this. I'll post this on Blackboard. But I'll just leave it up here for now. So these are the most important trig identities that you're going to need to solve these integrals. So let's talk about a general strategy for solving them.
There just also equal.
Oh yeah, so So there's three different ways to rewrite cosine 2x. So these are all cosine 2x. Yeah, that's a good point. Right, so let's talk about approach. For trig integrals. Yep. All right, so the first thing is identity. So the first kind of two things are usually what you have to do is you're rewriting the form of the given integral. And the first thing that's helping you rewrite the form is these identities, right? So you're applying these identities to get the integral in another form. The other thing is just a lot of algebra, okay? So with identities and algebra, you're rewriting the given integral, okay? You're rewriting the given integral. In order to do what? Well, in order to get like just an easy trig antiderivative, or to set it up for undoing the chain rule. That's basically what happens with these. Formatting is getting me here. How do I... Nope. Nope. All right, we'll just put 2 here. All right. Okay, so then most of the time it's going to be to get undoing the chain rule. But sometimes it's just, you'll just get an easy trig antiderivative. For instance, you'll do some identities in algebra and you'll get cosecant cotangent. Integral cosecant cotangent. And so with all our antiderivatives, we think, what function has that derivative? What function has the derivative cosecant cotangent? Anybody remember? She remembers. You guys remember what function gives you a derivative cosecant cotangent? So cosecant gives negative cotangent cosecant, so then your antiderivative would be negative cosecant. So that's an example of getting an easy trig antiderivative. So you really have to know your trig derivatives. But lots of times we'll be undoing the chain rule with these trig functions. So let's see some examples. Okay, questions on the approach. We're rewriting using identities in algebra, and then in order to get an easy trig antiderivative or set up undoing the chain rule. Okay, so let's do, here's the first easy example. Integral cosine squared x, tangent squared x, dx. So what could we do with this? So there's several things we could do with this. There's different ways. We can write cosine squared a different way. We could write tangent squared a different way. So there's a lot of trial and error involved too. But we're looking to either make this thing simpler or set up undoing the chain rule. So is there something we can do that will make it simpler? Yeah, so a common technique is to always rewrite tangents and cotangents in terms of sine and cosine. So if we do that, right away we see a nice result here. What happens? Cosine squares go. They become 1. So then we have sine squared x dx. So sine squared x dx is just one that you have to remember how to do it, and also cosine squared. And it comes up throughout the semester, and it comes up a lot. So where on here could we get some help? So it's another identity now. Where on here could we get help with sine squared? So we could, sometimes we'll rewrite sine squared as 1 minus cosine squared from the Pythagorean identity. But that just kind of puts us back in the same boat we were. Instead of having sine squared, now we have cosine squared. So down here, if you notice the half angle formula, sine squared equals 1/2, 1 minus cosine 2x. And that's easy. Antiderivative of, so we could factor out the 1/2 to start with, or we could factor it in, but antiderivative of 1, antiderivative of negative cosine 2x. So we're going to have sine 2x, 1/2 to take care of the 2, minus or plus. So the derivative of sine is positive cosine, so that negative just stays. Okay. So here we use the identity for tangent squared. That got us the cosine squareds to reduce away, leaving us sine squared. And this is just saying you have to remember, the integral of just plain sine squared or just plain cosine squared, use a half angle identity. Use a half angle identity. So that you just got to remember that. Okay, so what about, let's look at sine cubed then. Sine cubed. So we know sine squared, half angle, but sine cubed is a different story. How would we do sine cubed? Okay, he's got an idea. He said, let's try sine squared times sine. So here's where we want to start looking for undoing the chain rules. Can we see how we can keep going with this so we can set it up for undoing the chain rule? Anyone see what we could do?
Can we make sine squared cosine squared of x minus 1?
1 minus?
1 minus cosine squared of
Okay, a
x.
couple of you have had this idea, so let's take a look at it. So now we can think about distributing sine to both of those. Sine times 1, piece of cake, right? And then the other one would be cosine squared times sine. Can we do the antiderivative of that? Should be able to. So this is the same as sine x minus sine x times cosine squared. Do we recognize what we got there? Yeah, John?
I'm kind of confused on the half angle. So we're not using the sine squared x equals 1/2, 1 minus cosine.
Not here, because what would happen? If we plug this half angle in here, then we get cosine 2x. So then we'd have a cosine 2x and a sine x. So we have different angles going into our, and that kind of makes it impossible to do an antiderivative.
Okay,
So you only use it if it's just sine squared or just cosine squared is when you use the half angle formula. But here this is sine squared times another sine. We put the half angle formula in there, we got two different angles we're dealing with. We're dealing with 2x and x, and that kind of makes us, we're stuck. We can't go do anything with that. When we do these, we want to have the same angle in every single trig expression. We want to have the same angle. Is that good?
Yeah.
Okay. So antiderivative of sine x is negative cosine. And now, how are we going to do sine x times cosine squared? Apply what we've learned here. Apply what we've learned. Yes?
It's just cosine to a power, so you just up the power.
That's it. It's just, yeah. So you're going to do cosine what?
Cubed.
And then also 1/3. And then the derivative of cosine is minus sine. Well, here's minus, so should this be plus or minus? That should be plus. And always, if you're not quite sure, what can you do?
Check.
But take the derivative. Take the derivative, right? So don't feel anxious that you've got to write it down perfectly the first time, because we always know that we can take the derivative and check. So let's just do it for that second one. We get 3 times 1/3. This is our derivative. 3 times 1/3 cosine squared times negative sine, right? And is that what we have there? Yep, negative sine x cosine squared x. Got it, check. So we can do plus c here, plus c, and we're done. Anybody have a question? Okay, let me give you a couple just to work on and see how they go, okay? I'll do that soon.
So like there are two strategies.
Oh, I see. Thinking of it like that because I don't know how to deal with anything above the second power. So maybe that's the only way we'll be able to move it.
Yeah.
You don't, you probably keep that as tangent second, but at least take out the two secant squares. And that equals tan squared minus 1.
It's only if it's just cosine squared or just sine squared. It's not.
Is it because it's
that 2 sin x attached?
Yeah. So this is not cosine squared. This is sine x times cosine squared. To use the half angle formula, if you have the antiderivative of cosine squared, that's it. If it's cosine squared times something else, or plus, or divided by, that's
No, I can't solve that.
probably not half angle anymore.
I tried 2 different ways.
It's only if it's just antiderivative of cosine squared or antiderivative of sine squared. Anything more multiplied by it, probably not going to be half angle. Done doing the check. Exactly. That's what we got. Yep.
I don't think that's right.
Yeah.
I didn't take the do the integral at in third part. I went a step further and did 1 minus sine squared x and plug that in. Should I just stop and try to do the integral?
So you're going.
Yeah, I just went.
It makes it worse because then you have sine times sine squared. Now you're at sine cubed.
Oh, you're right.
So that you're kind of going. You're going the wrong direction, right? So you're going kind of making it. So this is already. Undoing the chain rule is always the first thing you look for, and what you're trying to set up. Already from undoing the chain rule, you're ready to do the antiderivative.
I just wonder if is that completely wrong or is it just a lot of harder work?
Yeah, I mean we did sine cubed in the previous example, so yeah, so you have 1 minus sine squared multiplied by sine. Now you've got sine cubed, and then you have to do that whole problem again.
Oh, you can't just take the integral of that.
Well, in the previous example, it took some work to do the integral.
Right. Okay.
Right? So we had to work it out. So it's like you're making it a lot harder problem than it needs to be. This is undoing the chain rule. Antiderivative, done. Okay, let me interrupt you. Any questions on the first one before I go to the second one? Any questions on the first one? Really turns out to be almost the exact same problem we just had in the previous problem. And so it's throughout all these techniques that we're doing in these 2 weeks, it's really so much of it is about undoing the chain rule, being able to recognize it and apply it. So it's the same thing again. Cosine quantity squared times sine is the result of a chain rule derivative. It's the result of cosine cubed over 3 times -2. Questions on the first one? Are we good? Okay, how's the second one coming? So it's a little more challenging, but once you see a couple like this, you can do them. So what did I give you? Secant to the 4th tangent? To the 7th, sorry.
He gave you a hint there by saying tangent.
So what we want to do is we want to think about, so let's just talk through all the derivatives of our 6 functions. So sine x, cosine x, tangent x, cotangent, secant, cosecant. Derivatives, ready? Derivative of sine. Cosine. Derivative of cosine. Negative sine. which is, for our purposes, essentially sine. We can always add a negative sign, a negative. Tangent x. Secant squared. Cotangent. Negative cosecant squared. Secant is secant x, tangent x, and cosecant is. So if we're undoing the chain rule, we're thinking about having one of these derivatives, right? If we can get one of these expressions as our f, right? So chain rule is the derivative of g of f of x. Chain rule says g prime f times f prime x. So we can, if we think of these derivatives as an f prime x, if we can get cosecant squared or secant tangent times a composite function that's based on this f. I'm having a hard time explaining this. Let's just do this example. So what can I pull out in this case that will be like our f prime of x? Okay, some people are saying secant squared. So if I pull out secant squared x, then I'm left with another secant squared and tangent to the 7th. So if I'm isolating the secant squared, if I can get this whole rest of this integrand in terms of what, then I've got undoing the chain rule, right? So what does this whole rest of the thing need to be in terms of? Times secant squared so that I have undoing the chain rule. Tangent. If I can get everything here, some powers of tangent, and that's multiplied by secant squared, then that's undoing the chain rule, right? So, can I do that? I've already got tangent to the 7th, so that's good. So I'm doing secant squared x. So, can I rewrite secant squared in terms of tangents? Well, it's tangent squared plus 1. And then I also have this tangent to the 7th. So now I'm going to distribute inside there. And I'll have secant squared tangent to the plus tangent to the 7th. And now look, I've got secant squared times tangent to a power, undoing the chain rule. And I've got secant squared times tangent to another power, undoing the chain rule. So I'm thinking secant squared. If I can get a secant squared out and get everything else written in terms of tangent, then I'm home free with undoing the chain rule. So this one will be, so this is tangent x to the 9th. And this is tangent x to the 7th, just so we're seeing it correctly. So let's this first term, secant squared times tangent x to the 9th. Antiderivative will be tangent x to the 10th with a 1/10. And so what's the derivative of that? That's tangent x to the 9th times secant squared. Similarly, I've got, so if we've got secant squared times tangent x to the 7th, the antiderivative will be tangent x to the 8th and 1/8. Let's see. Okay, so did you catch it? So to set some of these more complicated up for undoing the chain rule, it's like we're going to pull out that f prime term. We're going to pull out this f prime and look to write the rest of it in terms of its antiderivative. Okay, so try secant x times tangent to the 5th x. Last one. Secant x times tangent to the 5th. Let's see if you can do that one. if you're still, you can ask while others are working. If you want to ask about this one, is there any questions about this one? Yes, please. I have some more. Do it, but it's, well, first of all, it's not right. You have 2 sine x cosine squared. This isn't distributed, this is all multiplied. This is all multiplied together. You're not distributing, it's just 2 sine x cosine squared. So you have an extra cosine there. Just to cross it out. So you can, it's equal to this, but this isn't helpful for antiderivative because this angle doesn't equal this angle. Once you have things multiplied with angles different, you're stuck. You can't. You gotta have equal angles. So that is equal to this. It's just not helpful in the answer for it, right? So doing blue here. So what did I say? Secant times tangent to the 5th. So what are we looking for? We're looking for one of these derivatives to pull out and then get everything else in terms of its antiderivative. So what can we pull out? Right. Pull out a secant x, tangent x. Now we have times tangent to the 4th, and we want to rewrite that tangent to the 4th in terms of secant, right? So if I can rewrite tangent to the 4th in terms of secant, then I've got undoing the chain rule because I've got my derivative of secant, secant x, tangent x. So how do I write tangent to the 4th in terms of secant? Well, that's tangent squared squared. And what is tangent squared? So it's like 1 minus secant squared x squared. All right, we don't have time, but that will give 3 terms, but they'll all be thank you, sorry. So that tangent to the 4th becomes secant squared minus 1 quantity squared. That will give us 3 terms, right? 3 terms. Secant to the 4th, minus 2 secant squared, and then plus 1. And then we're home free because we can use undoing the chain rule for the last one and then for the first 2, and then that plus 1 times secant tangent, well, that's just secant. So do you see the roadmap to the end there? So now we've got it set up for, you're going to multiply this out, get 3 terms, and then you've got 3 antiderivatives that you can do using undoing the chain rule. And that last one's just secant tangent, which is antiderivative secant. Okay, same drill. Possible quiz on web work. Whenever we have web work, possible quiz. Be ready.